So we can continue. I'm introducing Jonas, and he will talk about how to find global minimizer for polynomial optimization exploiting the symmetric structure.
Okay, thank you. And many thanks for the invitation that I can present my research here. So this is ongoing work together with Victor Magor, where we look at polynomial optimization, where we want to exploit symmetry, and then we are asking the question how the classic minimizer extraction and flatness works in this framework. Okay, so let's jump right in. Okay, so let's just fix some notation maybe first. So we are looking at a polynomial optimization problem. We have a target polynomial f, which we wish to minimize, and we do this over a set which is also described by polynomial inequalities given by these gk. Okay, and then so we've seen this before. The moment relaxation at a given order t is defined by you want to construct a linear functional which takes input polynomials up to degree 2t. And then you want, so first of all, you normalize this linear functional by enforcing that it evaluates 1 to 1. And then the important part is you want the moment matrix to be PSD. Okay, and so the moment matrix, we will look at different bases throughout this talk here, will be indexed by the standard monomial basis. So you have an x to the alpha in the row, an x to the beta in the column, and then the corresponding entry would be L applied to x to the alpha plus beta. Okay, and then additionally, you have for the constraint polynomials, you also get these localizing matrices, which also have to be PSD, but they're not going to be so important for the context of this talk. So we will be focusing on the moment matrix. And the reason for that is that so a nice feature of this moment hierarchy is that under this rank stability condition, which is called flatness, you have a guarantee that in fact with your moment relaxation you hit the minimum of f, and further there are techniques how you can extract the minimizers of f. Okay, so this rank stability thing here, you can look at it as this moment matrix here. You index by lower degree monomials, so it sits inside of the moment matrix which you solved for. And if you then allow also for these higher degree monomials, you do not increase the rank of the moment matrix. And then the step size with which the rank has to stabilize, it depends on the degree of the constraining polynomials. But again, not so important for us here. Okay, and then the goal is going to be, we want to know how flatness and minimizer extraction works if you also exploit symmetries in your moment relaxation. Okay, so this is going to be the goal. So let's start with some facts on flatness and minimizer extraction. So suppose you solve your moment relaxation at a level t, and suppose that the rank stability, the flatness condition holds, then what do you get? So a couple of things happen. So what you can infer from this is that there exists a measure mu, and this measure mu is finitely atomic. So you have these Dirac measures here, which only put weight into the points uj. And your mu is just a finite convex combination of these Dirac measures. And you know that your linear functional in fact corresponds to this measure. So instead of plugging a polynomial p of small enough degree into your L, you can instead integrate with regards to your finitely atomic measure. And then furthermore, the support of this measure, the atoms of the finitely atomic measure, are precisely the minimizers of your polynomial f. Okay, so this is the first step. You have flatness, so you know that your relaxation is tight, and you know that your measure, the support of your measure contains information about the minimizers of your polynomial, but you don't have direct access to your to the measure. You only have access to the numerical data of the moment matrix that you solved. And in order to actually get access to the minimizers, we can observe the following identities. Okay, so we are interested in computing the support of mu. And what you can do is you can look at the ideal generated by the support of mu, so all the polynomials which vanish on the support of mu. And then this will coincide with the kernel of the infinite moment matrix. So why do I say infinite moment matrix? We only solved a finite relaxation order, but because we have a measure, you can extend your linear functional up to arbitrary degree. So this is the first identity of importance, and then this also relates back to the numerical data that you have in the sense that so this matrix MT, this is the thing you solve, this is what you have access to, and then if you look at the ideal generated by this kernel, this will coincide with the kernel of the big matrix. So everything put together, you're interested in computing the support of mu. You get a system of polynomial equations from the kernel of the matrix you have access to, and this is the polynomial system that you want to solve. And then you would get the minimizer of your polynomial optimization problem. Okay, and this is, let me try to alternate a bit. This is done usually with Stickelberger's eigenvalue theorem. We say a couple of words about this. So the key idea is you want to work in this quotient space, where you quotient from the polynomial ring the kernel of the moment matrix. And then in this quotient space, you want to consider the multiplication with the different xi. And what this will do is, because the quotient is going to be a finite dimensional vector space, and in fact, the basis of it you can just read from your moment matrix by looking at a maximally non-singular submatrix. So you can express this multiplication with these so-called companion matrices, MXI. And the eigenvectors and the eigenvalues of the MXI will give you information about the minimizers that you're trying to get. So this is this last equation here. Okay. Okay, so this is a very reduced summary of minimizer extraction if you have flatness. Okay, now we shift gears a little bit and we talk about symmetry reduction, and then we will hopefully put all the ingredients together. Okay, so let's talk about symmetry reduction for a bit. So what we are looking at is the case where we have a finite group G, which acts linearly on Rn. So think of a group of matrices acting on Rn. And then you can extend this group action to the polynomial ring. Precisely as follows. You have a group element, and then this acts on your polynomial f by inverting the group element and applying it to the input of f. Okay, and then just a couple more definitions here. You can now also define the invariant subspace of the polynomial ring, which are just precisely all the polynomials which are invariant under all group elements. On the dual side, you can ask for linear functionals to be also invariant under the group action, or another way of thinking of this is you want your linear functionals to be constant on orbits of polynomials. And then the third item here is the so-called Reynolds operator. So this projects a polynomial down onto the invariant subspace by forming the group average of the polynomial. Okay, and then there's going to be two different symmetry reduction techniques which are relevant to us. Okay, so from now on we will just assume that our polynomial optimization problem is invariant in the sense that just the target function and the constraining polynomials are invariant. Okay, and then there's two ways now to exploit this. So the first one is going to be that you can, without loss of generality, assume your linear function will be too constant on orbits by an averaging argument. And then you want to pick a smart basis which block diagonalizes your moment matrix, which would then give you a speed up if you try to implement this as a semi-definite program. The other method I know under the term of orbit space reduction. So the idea here is that you can express your invariant ring and these so-called fundamental invariants phi I. And then you can just recast the polynomial optimization problem in terms of these fundamental invariants and also the moment relaxation. So these are the advantage of this technique is that you get a decrease of the degrees that you need to implement your moment hierarchy. Okay, so those are two different techniques, and we are going to zoom in onto the first one now. And okay, so maybe I will try to go through this a little fast, just to give people the flavor of what goes on here. So the key idea is you can think of the polynomial ring as a representation of the group. And then, so first, unfortunately, you have to embed it into the complex polynomial ring. But then if you do that, you can apply Maschke's lemma, and you get this decomposition into isotypic components. So in the first step, you decompose the complex polynomial ring into these Wi, and these Wi will then further decompose into these Wij, and the Wij will be isomorphic as representations of G if and only if they share the same I. So you can think of the I's as the buckets where you put all the pairwise isomorphic representations. And then without loss of generality, we are always going to assume that for I equal 1, we just collect all the invariant representations. Okay, and then now comes maybe the step which is a bit heavy, which is that you can then in fact construct a so-called symmetry adapted basis for all these Wij. So we want a basis for the vector space Wij, so we need a third parameter which runs through the dimension of the vector space. And then this is going to be the elements with which we want to index our moment matrix. And okay, so our moment matrix at the very beginning was indexed by the standard monomials. Now suppose we are indexing by these elements of the symmetry adapted basis. And then what we plug this into is not just a linear functional as before, but we wanted to consider linear functionals which are constant on orbits of polynomials. And this amounts to, this is the same thing as requiring the linear functional to be only defined on the invariant subspace, and then first applying the Reynolds separator we saw on the previous slide. So this is just the same thing. Okay, and if you do all of this, and then you plug in the products of the symmetry adapted basis, what you see is this behavior that you get 0 either if the two i's are not identical, or you get 0 if the two u's are not identical. And if both of them are identical, you get these ci, jj prime, which in particular do not depend on the views. Okay, and if you okay, so this set might be a little hard to see on first glance, but nothing much is going on. So this moment matrix here with the hat, I will denote this way when we index with the symmetry adapted basis. And then what happens if you sort now in the symmetry adapted basis regards to the I and the U, you block diagonalize your moment matrix. That's the first information. So the blocks are here are written with this M to the I. And further, because your entries do not depend on the U, you get repeated entries with respect to the different U's. So this gives rise to this tensor structure where we hit our blocks with the in the tensor product with the identity matrix. So this might be hard to see on first glance, but I promise if one sits down and just reorders things by hand, you will just precisely see the structure. Okay, and this is of course nice because so this was our original moment relaxation, where we just have one big moment matrix that you're checking to be PSD. But now, of course, what you can do if you know you have this block diagonalization of your moment matrix, you can just check the individual smaller blocks. And of course, you wouldn't check the repeated blocks. You would only check each block one time for being PSD. So this is this condition here, and the same holds true for the localizing matrices. But okay, let's not focus on those. And then all of these things you can do without a loss of generality. So you're getting a computational speed up. Sort of for free. I mean, maybe you have to do some computations for the symmetry adapted basis, but on the STP level, you get this for free. Okay, good. Okay, so now it's time to put things together. Never mind. First, I wanted to show an example to make the symmetry adapted basis a little bit more concrete. So what we will be looking at today is only ever the case of sign invariance, because it's very straightforward to compute and see. So yeah, here's just an example for a polynomial which is invariant under the sign flip in X. It's a univariate polynomial. And then suppose you solve your moment relaxation. You have some linear function in L. What you can do is you can define a different solution, L tilde, where you take the original L that you had, and first you apply a sign flip to the polynomial. And this will also give you a solution to the moment relaxation. And then, in fact, what you can do is you can just look at the sum of those two together. And what you will observe is that if you evaluate the sum on even degree monomials, this will just behave exactly as the original L that you started with. But if you evaluate this on odd degree monomials, what you will see is that the L and the L tilde will just cancel. And then, so suppose this is our moment matrix at some truncation level T. And then what we do is we order all the even degree monomials in one bucket. And then what you can see in this block here is, so you're multiplying two even degree monomials together. So this will result in an even degree monomial. So you just get some entries here. You get some entries here because you're multiplying odd degree monomials together, resulting in even degree monomials. But in those two blocks here, you're multiplying even degree monomials with odd degree monomials, resulting in odd degree monomials, meaning that our linear function will be zero on this. Okay, and then this is precisely the block diagonal structure we had on the previous slides. Okay, and then of course also just to connect back maybe. So this here would then correspond to the invariant block, right? So those even degree monomials are the ones which are invariant under the sign flip. So this is what we collect in I equal 1. Okay. Right. So what we propose to do is we want to introduce this concept of block flatness. So suppose you are just solving your symmetry adapted moment relaxation now. So you're numerically speaking, you're just getting a bunch of smaller blocks of numerical data. And then what we call block flatness is that this condition, which if you were to ignore this I on top, just looks identical to the previous flatness condition. But now we are just asking for this condition to hold on all of the blocks at the same time. And if this is the case, we call our linear functional block flat, or we call the moment matrix block flat. And then what happens is that if this is the case, you get all the good things that happened in the classic flatness case now for the block flat solution. So if your solution is block flat, you know that you actually attained the minimum, and furthermore, you get this finitely atomic measure where the support will correspond to the minimizers of your polynomial. Okay, and the proof is also conceptually nice to mention. So the key point is you have to relate the two bases to one another, the standard monomial basis and the symmetry adapted basis. So let's say P is a change of basis matrix. And then the key identity which holds this together is given here. So this guy here is just the standard moment matrix indexed by the standard monomial basis. And then if you apply P and P transpose, of course, you transpose the indexing to the symmetry adapted basis, so you precisely get this block diagonalization. And then if you know that your solution is block flat, you can evaluate the... Somehow I'm creating an echo. If your solution is block flat, you can just evaluate the rank on the right-hand side of the equation easily, because it's just the sum of the ranks of the different blocks. And because P is invertible, your moment matrix will just share the same rank. So through the block flatness, you just get flatness of the classic moment matrix. And you get all the results sort of from that. Okay, so here's another example to see block flatness in action. So now we have two variables, x and y, but still things are invariant under symmetry in the two variables. The minimizers are clearly plus minus 1 and plus minus 1. And if you look at the linear function, it just plugs in those points. What you get is this moment matrix, which is x expected block diagonal, and you get that for the classic moment matrix flatness holds, as well as for all the individual blocks. Good. Okay, so let me try to motivate this next thing for a little bit. So the nice thing with block flatness is that if you solve your symmetry adapted moment relaxation, so you only numerically have access to these smaller matrix blocks. You do not have to do the bookkeeping or reconstructing the original moment matrix. You can just check for flatness only on the block level. And somehow one would now like to, ideally you could now also run the minimizer extraction only on the block level and then combining the information. So unfortunately, I don't think that works. The only block for which I can say something useful is the invariant block, so when I is equal to 1. But I think, fortunately, quite some useful things can be said about extracting on this level. So observe the following thing. So suppose we have block flatness, and then in the back of our heads, there's always the dense moment matrix, which corresponds to our solution, for which you know that this one can now be extended to an infinite moment matrix. And this would also correspond to the fact that the invariant block needs to be extended to an infinite size invariant block. So this is sort of happening explicitly. And one thing that we saw earlier was if you have your truncated moment matrix, that the kernel of this guy corresponded to the kernel of the infinite moment matrix. And this is a property we would also like to have for the invariant block. Unfortunately, one needs one more technical requirement, which is that the step size with which flatness occurs is at least as great as the biggest fundamental invariant. So that being at least this step size d phi. So this might look like a rather technical condition at this point, but we will later see why this is important. Okay, and then the second statement that I want to make is, so suppose you have your block flat solution, and you want to we focus now on the invariant block. So what you then can do is you can just run Stickelberger's eigenvalue method, which we saw on one of the slides at the very beginning. But just instead of doing these multiplication matrices in the just in the quotient space, you are now doing everything in the invariant subspace. But you can write down all the same statements. Things just work out algebraically identically. So this is why I can make statements about extraction on the invariant block, because there's this algebra responding to it. Okay, and then the question you might ask is, suppose you run Stickelberger's eigenvalue method now on the invariant block, what are we actually extracting? What kind of information are we actually getting access to? And this is the contents of this lemma. And maybe to summarize it in one sentence is, instead of just extracting minimizers, you're extracting orbits of minimizers. So remember these phi were the fundamental invariants, and in the case of our sign symmetry, they are just the squared variables. So in the previous example, the invariant polynomial ring. 2 minutes. Oh, Jesus Christ. Okay, buckle up, everyone. Okay, so in this previous example, we have the minimizers plus minus 1 plus minus 1, and the fundamental invariance would just be precisely x squared and y squared. So if you now look at this thing, what you would be, so suppose x is plus 1 minus 1, one of the minimizers, then phi of x would always just be 1, 1, because you're plugging it into x squared and y squared. So instead of extracting 4 different minimizers, you're just extracting the information x squared is equal to 1 and y squared is equal to 1. Okay, and then let me try to jump to the conclusion of what I wanted to say. So unfortunately, I will now have to skip over the orbit space reduction. Okay, but let me just try to convey the following lemma. So if we can extract now on the invariant block, you could also ask the question, what if we do not have block flatness, but we only have flatness in the invariant block? Then do we still get some guarantees, or what are we even extracting? And the new statement is now that if you have flatness only on the invariant block, you don't care about the other blocks, then in fact you already attained the minimum by constructing a solution which is flat in this orbit space reduced setting, which unfortunately I didn't introduce now, but you sort of, there's two different size reduction techniques, and you have to transfer the solution which is flat in the invariant block over to a solution which is flat in the orbit space reduced setting. And this works by using the sparse flat extension theorem by Monique Laurent and Bernard Morin. Okay, so this is the Canadian which I wanted to end. Now it was a little abrupt. I hope I still got the message across. Thank you.
For some question.
Does the structure of the group play any role in how effective symmetry exploitation becomes? Like, is there a class of groups that makes this really effective or not really?
Yeah, so broadly speaking, in polynomial optimization, there's only, I mean, there might be very abstract groups you could be exploiting in principle, but I feel like in practice it mostly boils down to either sign invariance or the symmetric group, so where you can permute the ordering of the variables. So for more abstract groups, it would work in principle, but I'm unfamiliar with the concrete examples.
Question?
So I was wondering, maybe related to this. So if you had something like minimized one, such that x plus y equals 1, or something like this, then you would have an obvious sort of a symmetry group with a sort of a substantial. And I was wondering whether you could sort of then do like an extension of the Curtin-Fialko or such to sort of say, if we have the flat extension in the sort of adapted as the problem, we can have like some adapted sort of measure. So it wouldn't be finitely atomic in the original spec,
Right.
in the original problem, but it would be finitely atomic in the new adapted sort of a setting.
Yeah, so
I think that would be cool, right?
Yeah, so this is precisely what happens. So so one thing I should specify is, if you rewrite your problem with these fundamental invariants, I'm for now assuming that there's no algebraic relation between these generators. But then this space just, in fact, looks like a new polynomial ring, just a new variables, and Curtin-Fialko would just work. So if you transfer the solution over to this orbit space reduced setting, you use this sparse flat extension theorem, then precisely what you do in the next step is you use Curtin-Fialko, and you get a measure on this on these fundamental invariants. But I think you could then also translate this back to a measure in the original setting, and I think
but then it would be,
no, it would be unique.
what would be original space? Like in the example where you would have like x plus y equals 1 and a constant object. Right? So sure, I think that you could my claim is that you could do generalizations of Curtin-Fialko, which wouldn't be sort of like unique finitely
Right.
atomic measures in the original space.
Right. So you would use
You
the
would have a non-finitely atomic sort of representing measure in the original frame,
right.
which would be finitely atomic sort of and unique in the adapted sort of
Right.
setting.
I see what you're saying. So
I think that would be cool.
yeah. So what happens is you're precisely if you had degrees of freedom before because you could have many minimizers in the original setting, but then all of them get reduced to one orbit,
Yeah,
right?
you could have like infinitely many minimizers originally, sort of a finitely atomic representing measure, but you would have like one orbit in your adapted sort of a setting, and
That's a very nice question. Yeah, thank you.
Okay, we have time for a very brief question. Yes.
So in the open space case, so rigidity Schwarz works well if you have a reflection group, okay? Because then you don't have to add any new relations. There is no relations that you have probably on your ring. But if you don't, then you have to add a lot of new relations in the generators, right?
Why would you need new relations in the gen? Okay, but I mean, one thing that I skipped is, so you would now get a measure in the orbit space reduced setting, but then of course you need to make sure that the support of this measure is realizable, so that the J of the support is PSD. But this you can show using the moment data, not of the invariant block, but the moment data of the other blocks. But I didn't. Yeah, I can show you.
Okay, that's running out the time. So this concludes our session, and let's have some lunch.